Welcome to this explainer. Today, we're going to break down the fundamental physics of fluid motion. We are jumping right into a structured, step-by-step masterclass on one of the absolutely most fascinating and critical properties in all of fluid mechanics. I'm talking about viscosity. Whether you're designing massive municipal pipelines, engineering a high-speed hydroelectric turbine, or really just trying to make sense of the physical world around you, mastering Newton's law of viscosity is an absolute must. So let's get into it. Here is our quick roadmap for today. We're going to cover Introduction to Viscosity, Newton's Law Explained, Units and Fluid Types, Solving Engineering Problems, and finally, Real-World Applications. All right, let's kick things off with Section 1, Introduction to Viscosity. Picture this. You're standing in a laboratory, and on the table right in front of you are two clear glass bowls. One is filled with ordinary water, and the other is filled with thick, golden honey. Now, if you drop a small metal ball into the water, you already know exactly what happens, right? It sinks to the bottom almost instantly. But if you take that exact same metal ball and drop it into the bowl of honey, well, we instinctively know the ball falls much, much slower. The honey is literally fighting back. It's offering a significantly higher resistance to the motion of that ball. So, the crucial takeaway here is that this everyday thickness we observe is formally defined in fluid mechanics as viscosity. Whenever a fluid flows, its internal layers physically rub against one another, creating friction. It's like a giant microscopic traffic jam. A fluid with low viscosity, like water, flows super easily. But a fluid with high viscosity, like our honey, resists that flow with a whole lot of internal friction. Moving right along to Section 2, Newton's Law Explained. To actually visualize this scientifically, I want you to imagine a super thin layer of fluid perfectly trapped between two flat parallel plates. Now, the bottom plate is fixed. It's bolted down. It cannot move. The top plate, however, is being pulled forward at a constant speed. So what happens to the fluid sandwiched in between? Well, the layer of fluid physically touching the bottom plate actually sticks to it. Its velocity is absolute zero. Meanwhile, the layer touching the top, moving plate gets dragged along at maximum speed. And those fluid layers in the middle? They move at intermediate speeds, getting faster and faster the higher up you go in the gap. This steady, progressive change in velocity over a specific distance is what we call a velocity gradient. In calculus terms, we express this as dv over dy, which is also known as the rate of shear strain. Now, because these adjacent fluid layers are sliding past each other at totally different speeds, they generate a friction-like resistance. Sir Isaac Newton actually observed this exact phenomenon and gave us a brilliantly simple foundational rule. The shear stress, which is the resisting force per unit area between these layers, is directly proportional to the rate of change of velocity with respect to distance. And that insight brings us directly to our primary equation for this masterclass. Tau equals mu times dv by dy. Let's meticulously break down those variables. Tau represents the shear stress, and we measure that in newtons per square meter. Our dv by dy, like we just mentioned, is the rate of shear strain measured per second. And that leaves us with mu, our dynamic viscosity. Mu acts as the proportionality constant here. It is literally the mathematical embodiment of a fluid's unique thickness or personality. Okay, let's jump into Section 3, Units and Fluid Types. Now, here's a fun fact. Not all fluids play by the rules. We generally categorize fluids into two main camps. Newtonian fluids are the well-behaved ones. They follow Newton's law exactly, meaning their shear stress is directly and linearly proportional to the rate of shear strain. Water, air, and gasoline are classic textbook examples. Non-Newtonian fluids, on the other hand, they actually change their viscosity depending on how much shear stress you apply to them. Think of ketchup. It famously refuses to pour until you smack the bottle, applying a stress that temporarily thins it out. Blood and paint do this too. But actually, scratch that. Let's look at honey. You might assume honey is non-Newtonian because it's so gooey, but it's actually a purely Newtonian fluid. Even though it's incredibly thick, it still follows the linear relationship of Newton's law perfectly. It just happens to have a naturally massive value for its dynamic viscosity, mu. Let's quickly formalize our units so our math is rock solid. If we rearrange our main equation to solve for dynamic viscosity, our mu, we simply divide the shear stress by the velocity gradient. This mathematically leaves us with the standard SI unit of Newton seconds per square meter. However, just a heads up, in older engineering literature, and honestly in a lot of practical applications today, you'll frequently see dynamic viscosity expressed in a unit called poise. Don't let it trip you up, it's a super easy conversion. One poise is simply equal to 0.1 newton seconds per square meter. Now, while dynamic viscosity tells us all about a fluid's internal friction under sheer mechanical stress, many fluid flow calculations, especially those involving gravity and pressure, like water flowing through a city pipe, require us to know how that fluid's momentum diffuses. To find this, we simply divide the dynamic viscosity, mu, by the fluid's density, rho. This gives us what we call kinematic viscosity, represented by the Greek letter nu. The SI unit here is square meters per second. But just like poise, it has an older common unit called stokes, where 1 stoke perfectly equals 10 to the power of -4 square meters per second. All right, section 4, solving engineering problems. It is time to step into the shoes of a veteran engineer and crunch some numbers. Let's tackle our first scenario. We need to find the mechanical power required to pull a flat, 1 square meter plate over another plate at a speed of 0.3 meters per second. The tiny fluid gap between them is just 0.1 millimeters, and the fluid's viscosity is given as 1 poise. Okay, step 1. We convert that 1 poise to standard SI units, giving us a mu of 0.1. By carefully applying our equation, multiplying our 0.1 viscosity by the velocity of 0.3, and then dividing by our tiny distance, which is 0.1 times 10 to the -3 meters, we find a shear stress of 300 newtons per square meter. Now, multiplying that stress by our 1 square meter area gives a total shear force of 300 newtons. Finally, to find power, we multiply force times velocity. 300 newtons times 0.3 meters per second results in an incredibly straightforward 90 watts of required power to pull the plate. How about we reverse engineer a system? This time, we know the plates are 0.03 millimeters apart. The relative speed is 0.5 meters per second, and the measured shear stress is 1.8 newtons per square meter. Our job is to identify the fluid. So we rearrange our formula to solve for mu, shear stress multiplied by dy over dv. Plugging in our known values, we calculate a dynamic viscosity of 1.08 times 10 to the -4 newton seconds per square meter. What does this tell us? Well, in this scenario, we discover that such a remarkably small dynamic viscosity value means we are dealing with a very thin, highly active fluid, most likely a light mechanical oil or even just water. Now let's apply all of this to a real piece of heavy machinery, a journal bearing. Imagine a rotating steel shaft with a 0.12 meter diameter spinning at exactly 200 revolutions per minute. The lubricating oil has a viscosity of 0.1 SI units, and the clearance gap, RD, is 1.25 millimeters. First up, we have to calculate the tangential speed of the spinning shaft. We do this by taking pi times the diameter times the RPM and dividing that all by 60. This gives us a surface velocity of 1.25 meters per second. Boom! Now we have our velocity gradient. We multiply our viscosity of 0.1 by that velocity gradient, ultimately yielding exactly 100 newtons per square meter of continuous shear stress inside that machine's bearing. Let's look at one final, really elegant problem that combines density and viscosity. We have a fluid with a specific gravity of 2.2 and a kinematic viscosity of 5 times 10 to the -4 square meters per second. The question is, what is its dynamic viscosity? Step 1 is finding the actual density. Since standard water is 1,000 kilograms per cubic meter, a specific gravity of 2.2 means our mystery fluid's density is simply 2.2 times that, or 2,200 kilograms per cubic meter. Next, we grab our kinematic formula, nu equals mu over rho, and rearrange it. Multiplying our given kinematic viscosity by our newly found density flawlessly converts specific gravity into a true dynamic viscosity of 1.1 newton seconds per square meter, or if you prefer the classic units, exactly 11 poise. And that brings us to our final segment, section 5, real-world applications. So why does all this rigorous math actually matter? Well, it matters because viscosity dictates the literal physical limits of human infrastructure. When civil engineers design municipal water supply networks, they must precisely calculate friction losses in the pipelines, and those losses are entirely governed by the water's viscosity. Viscosity dictates everything from how efficiently a giant hydroelectric turbine spins to exactly how much mechanical energy is wasted as heat when pumping crude oil thousands of miles across the country. It even dictates how heavy sediment is transported down natural rivers, or how fast groundwater seeps through the deep soil mechanics of a skyscraper's foundation. It is literally everywhere. But hey, there is a crucial environmental caveat you must always keep in mind when engineering. These fluid properties are highly temperature sensitive, and they don't all behave the same way. For liquids, as you add thermal energy and increase the temperature, the fluid flows much more easily, meaning its viscosity decreases. But fascinatingly, for gases, the exact opposite is true. As a gas heats up, its molecules start colliding much more violently with each other. All that chaotic bouncing around causes the gas to actually thicken and increase its internal resistance to flow. No way, right? But it's true. Ultimately, understanding viscosity is truly like understanding the unique personality of a fluid. Some fluids are lazy and highly resistant with high viscosity, while others are hyperactive and free-flowing. But once you decode their personality through Newton's law, you hold the mathematical power to predict exactly how they will behave in literally any pipe, pump, or channel on Earth. So the next time you pour cooking oil into a pan, or even just watch water flow from your kitchen tap, I challenge you to look closely at its velocity gradient and ask yourself, what is the true personality of this fluid? And armed with everything we've learned today, how would you measure it?